Hello again, welcome back. So here I have some stuff written down in a recording go bad, so we'll just take a look. I have this function r of x, which is x plus 2 divided by x squared minus 9. What I want to do is I want to find its domain. One problem with domains is when you have a denominator, because a denominator can't be 0. So what you do is if you have a denominator, you take it and set it equal to 0. Here, one way to solve is to add 9 to the other side, taking the square root of both sides. Square root of a square leads to plus or minus. Square root of 9 is 3. So there's two numbers that make the denominator 0. They cannot be in the domain. So then I can say the domain is any real number except 3 or negative 3. On the number line, I would have an open circle at negative 3 and an open circle at 3, meaning I can't use those. But I could shade any other number as fair game to plug in here. That means I have 3 different regions. As far as interval notation goes, the left region is from negative infinity to negative 3. Always go in order. Union from negative 3 to 3, union 3 to infinity. So that's the range of this function. So the last video we saw that a square root gave us problems with domain. Here, denominators give us problem with range. Otherwise, there's not too many other problems, at least at this point in time, based on math that you're familiar with so far. So for many functions, domain's all real numbers, unless there's a denominator that could, not always, but it could lead to domain restrictions. Square roots also sometimes lead to domain restrictions, not always. Okay. Alright, let's try another function. How about f of x equals x cubed minus 3x plus 5, and we want to examine this on a calculator on the interval where x is in negative 2 to 2. And you've seen problems like this on the homework. You were given an x interval that'll also state something like y is between negative 4 and let's say 10. So I'll have to enter this in the function menu, this and this for the window. And then you were given a picture in the homework to say which picture matches the graph on your calculator. There'll be a question like this on the test too. So let's see, calculator, clear that sucker. And I want x raised to the 3rd power minus 3x plus 5, that looks about right. Window from negative 2 to 2, scale by 1 should be okay. And then negative 4 to 10. Hopefully this allows me to see some interesting features of the graph. There it is, it does a little wiggling there. Notice this function has a maximum and has a minimum. It may be that point on the edge of the interval is lower than that, but in this region that's the lowest point. If you were walking along, you'd hit that bottom and then you start to climb again. If you're walking along, you hit that high point and then you start to drop down. So these are what are called relative max and a relative min, probably. Right, so let's see if we can identify that. So what we want to do is say, when is this function increasing? Well, right up to there. When is it decreasing? From here to here. And when is it increasing again from there to there? So we need to identify that max and that min. Algebraically, there's no easy way to do this at this point in our lives. So what we're going to do is use the calc menu. And I'm going to do the maximum first on the left side. Alright, so my max is over here. I need to get to the left of it. Roughly to the right of it. Enter. and in the middle. Okay, wow, it looks pretty darn close to -1, so I'm going to say at the point -1,7 I have a max. So f of x has a max of 7, that's the y value, when x equals -1, would be one way to phrase that. The max is the y value, because the function is a y value. Remember, y equals f of x. Okay, and then for the min, we just repeat that for the minimum. So second calc, minimum, tracing over to the left, out there, good enough, and to the right, and then near the middle, or near the min. Okay, and it looks like it's at 1,3 roughly. And just to double check, I could hit trace 1, enter, I get 3. If I type, what was it, 0.9999987, something like that. Oh, it still gives me 3, but it's not really. Trust me, it's actually 1,3. It's a weird thing about calculators, they don't give you exact answers some of the time. So f of x has a minimum of 3 when x is +1. Okay, so here I have the point -1,7, and I think 7 is the max of the function in that region. It may get bigger elsewhere, but not in that region. And then 1,3, I think 3 is the min of the function. The nice thing there, if I just do a rough sketch of the function there, this point here, x equals -1, separates, because on this side I am increasing. And then when x equals 1, remember, function depends on x, so a lot of things we state in terms of x. After 1, the function is increasing again, but in between, this part of the curve is what we call a decreasing part of the curve. We're decreasing between -1 and 1. So on the computer, the last when is the function f of x, let's say increasing. F of x is increasing. Let's see, can we see that on here still? Yeah. When x is in the interval from -infinity to -1, union 1 to infinity, right? This chunk and that chunk. We're decreasing, however, f of x is decreasing when x is in the interval from -1 to 1. Now here that's not a point, that's interval notation. We use context to differentiate. Okay, so we can analyze when a function's increasing, when it's decreasing. We can find minimums and maximums. Pretty cool, huh? Alright, let's see, do I have time for one more here? I do. Let's take a look at what's called a piecewise function. And if you have any questions on any of this, the take-home the practice test, that sample I posted, get in touch with me. Alright, so last problem of the night, or day, wherever you are in the future. Let's take a look at f of x equals -2x plus 3 if x is less than 1, 4x minus 3 if x is greater than or equal to 1. So that's what's called a piecewise function. Because on this part of the domain I use that to get points, on this part of the domain I use that. So to do this I'm going to make a table. This is not easy to plug into the calculator. And here I want numbers all the way up to 1. So that would be numbers like I don't know, -3, -2, 0. Let's go all the way to 1. Even though I technically can't plot that point because it's less than. But I can put an open circle there. And you'll see what I mean in a minute. If x is less than 1, which is all these numbers, then I can plug them in. So -3 plugged in here gives me 6 plus 3, I think it's 9. If I'm wrong, please correct me in the future. -2 times 2 is 4, plus 3 is 7. 0 gives me 3. Now I'm going to plug in 1. That's a special point. That goes with the less than, because it's a boundary. I go right up to the edge of 1. If I plug in that, I get what? 1 back. Alright, so let's just graph that chunk right up to 1, 1. So 1, 2, 3, all the way up to x equals 1. I'm going to put a little dotted line here to indicate my function changes, the definition changes after that line. And I need to get up to 9, so I better scale a little smaller here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 9. So I want to point right about there. -2 goes with 7, right about there. 0 goes with 3, and 1 goes with 1, right about there. Oops. And at the moment, that needs to be an open circle, and this should be a straight line, right? So I whip out my straight line tool, whatever that happens to be, and draw my best straight line there, make the point bigger if it didn't hit. Okay, open circle means I can go right up to the edge. Notice it says less than 1. Stopping at 0 wouldn't be good because 1/2 is less than 1, 0.75 is less than 1, x equals 0.9 is less than 1. I can go right up to the very edge of 1, and that's what that open circle is for. Alright, other part, let's graph this part. I can graph that part if x is greater than or equal to 1. So in the second part of the table, I'll start at 1, 2, 3, and plug them in. Plug in 1 there. 1 times 4 is 4, minus 3. Oh, look at that, I still get the point 1, 1. Sometimes the pieces do meet at the same point, sometimes they don't. 2 times 4 is 8, minus 3 is 5. 2 times 4 is 12, minus 3 is 9. Okay. So 1, 2, 3 is about here, and I have this point right there. 2, 5 is about what there? 3, 9 is somewhere over here, and again my points kind of line up. Oh, look at that, it's beautiful. And I believe it continues that way forever. Isn't that a cute graph? A little skewed V. I love that. If you're really geeky about math like me, you'd kind of wonder, what's that angle right there? Turns out there's a way to find it. We're not going to worry about it right now. Alright, so that is a piecewise function. The way you do it is you make a table for this part of the domain using that formula. Make a table for this part of the domain, use that formula. If there was a third part, I would just make another table. Plot each part independently. Sometimes they connect, like here they do, sometimes they don't. Sometimes you get piecewise functions where one piece could be curved and ends there, and the other piece might pick up right here and be relatively straight. All different kinds of animals out there, mathematically speaking. Alright, that's enough for now. Get busy on your homework, get busy on that practice test. You got to take the practice test before you take the real test. Take it until you get 100% or as close as you have time for. Get in touch with me if you have any questions or concerns. If you want to meet up soon and do some math, let me know. A relatively flexible schedule. Over and out.